How deep is the ocean? How much of Earth is covered by the global sea? These are basic questions, but they went unanswered for thousands of years. People's interest in the oceans undoubtedly dates back to ancient times, but it was not until rather recently that these seemingly simple questions began to be answered. Hello everybody, this is Trisha Neglisha reporting the vast world of the oceans. Calling Earth as the water planet is certainly appropriate because nearly 71% of its surface is covered by the global ocean. Important term to remember in this chapter is oceanography. Oceanography is a composite science that draws on the methods and knowledge of biology, chemistry, physics, and geology to study all aspects of the world ocean. The vast world of ocean. A glance at a globe or a view of Earth from space reveals a planet dominated by the world ocean. It is for this reason that the Earth is often referred to as the blue planet. By studying a world map, it is readily apparent that the north and southern hemisphere are not evenly divided. The northern hemisphere is referred to as the land hemisphere because 61% of its surface is water, while 39% is land. While the southern hemisphere referred to as the water hemisphere because 81% of its surface is water, while 19% of it is land. And among the three major oceans, Pacific is by far the largest because it is like an Atlantic and Indian Ocean combined. Seawater is a complex solution of salts consisting of about 3.5% by weight dissolved mineral substances. Although the quantity may seem small, or the percentage, it is actually huge. If all the water is evaporated from the ocean, it would pile up to 60 meters thick, covering the entire ocean floor. Salinity and its variations. Now we have reached to salinity and its variations. So salinity is the total amount of dissolved material in water, and it is expressed as parts per thousand or percent. Average salinity would be 35%, but in surface salinity in open oceans, it's actually ranging from 33% to 38%. And principal elements contributing to salinity would be, of course, sodium chloride. Sodium is 31% and chlorine is 55%. And there are many factors affecting to the salinity of water. The following are the processes that decrease water salinity: precipitation, runoff from land, icebergs melting, and sea ice melting. So those mentioned processes affect salinity by decreasing it because it is adding water to the ocean water. And processes that increase water salinity: evaporation and sea ice formation. And of course, those mentioned processes increase the salinity of water because it is removing water while concentrating materials that are dissolved in it. Sources of sea salts. We have always known that seawater is salty, but have you ever wondered what makes it salty? What are the sources of it? So there are primary sources of sea salts, namely the chemical weathering and the outgassing. Chemical weathering of rocks on the continents is one source. These soluble materials are delivered to the oceans by streams at an estimated rate of more than 2.5 billion tons annually. The second major source of elements found in ocean water is the Earth's interior. Through volcanic eruptions, large quantities of water and dissolved gases have been emitted during much of geologic time. This process, called outgassing, is the principal source of water in the oceans as well as in the atmosphere. Certain elements, notably chlorine, bromine, sulfur, and boron, are much more abundant in the ocean than in Earth's crust. Because they result from the outgassing, their abundance in the sea tends to confirm the hypothesis that volcanic action is largely responsible for the present oceans. But why doesn't the sea get saltier? Obviously, because materials are being withdrawn are removed as rapidly as they are added. Some are turned into sediment during precipitation, and some plants and animals you actually needed it. And yeah, seawater, its saltiness is constant. And if you are curious about how to make a seawater, you can actually come up with artificial water, of which I will give the recipe in the next slide. The recipe for artificial seawater. Resources from seawater. So my report is coming to an end, concluding in resources from seawater. So commercial products found or obtained in seawater would be the common salts, of course, the sodium chloride, metal magnesium, bromine, and of course, you won't believe it, fresh water. And I will tell you plainly in the next slide why we can get and how we can get fresh water from seawater. Magnesium and bromine. For many years, seawater provided a high percentage of the world's magnesium and bromine. In the late 1960s, 70% of the world's bromine and 61% of the world's magnesium came from the chemical processing of seawater. Common salt or sodium chloride. Ever since ancient times, the ocean has been an important source of salt for human consumption, and the sea remains a significant supplier. To obtain pure sodium chloride, evaporating ponds are used. Lastly, fresh water. One of the resources derived from seawater is fresh water. The removal of salts and other chemicals from seawater is termed desalination. The purpose of this process is to extract low salinity or fresh water suitable for drinking, industry, and agriculture from water that is so saline that it is not suitable for these purposes. However, the cost of desalinated water is still much too high for crop production.
A continuation of the ocean environment. Learn about the submarine canyons and the turbidity current, the ocean basin floor, and the mid-ocean ranges. So let's proceed to the submarine canyons and the turbidity currents. So what is submarine canyons? So it is the cut into the continental slope and may extend across the entire continental rise to the deep ocean basin. While the turbidity currents, it is the downslope movements of dense, sediment-laden water beds deposited by this silt and clay. Consequently, these deposits called turbidities. So here are a brief explanation of the submarine canyons and the turbidity currents. And turbidity currents, underwater avalanche carries sediment downslope. Submarine canyons and fan-shaped deposits are formed. Erosion of shelf is caused by earthquakes, collapsing slopes, and other disturbances. And now, let's move on to ocean basin floor. There are the deep ocean trenches, the abyssal plains, and the seamounts. So first, the deep ocean trenches are long, relatively narrow features that form the deepest part of the ocean. The second one is the abyssal plains, are incredibly flat features. In fact, these regions are likely the most level places on Earth. The third one is the seamounts. Dotting the ocean floors are isolated volcanic peaks called seamounts. Here are the brief explanation of deep ocean trenches. So this is the Marianas Trench. They are typically 50 to 100 kilometers wide and 3 to 4 kilometers below the level of the surrounding oceanic floor and thousands of kilometers in length. There are about 50,000 kilometers of oceanic trenches worldwide, mostly around the Pacific Ocean. Also in the Eastern Indian Ocean and a few other locations. The greatest ocean deep measured is the Challenger Deep of the Marianas Trench with 35,813 feet or 10,915 meters below sea level. And now, the second topic of the ocean basin floor is the abyssal plains. It is a flat region of the ocean floor, usually at the base of a continental rise. The third one is the seamounts. It arises at least 1,000 meters of the surrounding seafloor. It estimated there are over 100,000 of these seamounts globally. Most of where are the extinct volcano. In some cases, seamounts reach above the surface to form a volcanic island. An example of this is an Hawaiian Big Island, where its volcano Mauna Kea. It's a peak of a massive underwater that rises over 10,210 meters. That's taller than Mount Everest. However, these islands can be seamounts again if the volcano become a storm across a billion of years. Erosion and subsidence may cause the island to sink beneath the ocean surface, and in some cases form a special kind of flat-topped seamounts. Seamounts offer important structures to live to form a different ocean zone. And now, my last topic, which is the mid-ocean ridges. Our knowledge of mid-ocean ridges comes from sounding taken of the ocean floor, core samples obtained from deep sea drilling, visual inspection using deep diving submersible. Some plates crash together. Others tear apart. It happens under the ocean, like here in the middle of the Atlantic. Lava erupts at the boundary between two crystal plates, sealing the tears. This is the Mid-Atlantic Ridge, a 10,000 miles tear on the floor of the Atlantic Ocean. The ridge is a mine of an underwater volcanoes, and it's here the new oceanic crust this form it stretches from South Atlantic all the way to Iceland and the north, where it rises above sea level. From the year the Mid-Atlantic Ridge is an autumn sight. This dramatic scarn in a landscape marked the boundaries between North America, coastal plate on the left side, and the European plate on the right side. The gap between the two ocean plates is filling in the ancient of year. Part of the ridge's movement is earth crust reshaping our world. And further, along the axis of some segments are deep down faulted structures called rift valleys. So there are the formation of the rift valley. Rift valleys forms where earth tectonic plates move apart or rift. Rift valleys are found on land and at the bottom of the ocean. They are formed due to the sinking of land between two normal faults or deep slopes. Here's an overview of ocean floor features. So there are the continent, the continental slope, the seamounts, and then the abyssal plain, and here are the mid-ocean ridge, the trench, and also the continental shelf, and this is the island. Thank you for listening.
Good day, I am Bea Bundasto and I'll be discussing the ocean layered structure. Oceanographers have found that temperature and salinity vary with depth. They recognize a three-layered structure in the open ocean, which are the surface mix zone, a transition zone, and a deep zone. First, let's talk about the surface zone. This is where the ocean receives the sunlight. This zone goes over 200 meters below the surface of the ocean, and the sunlight zone is warmer than the layers below it. And plants can grow there because the sunlight can reach them, which they can use to make foods. Because of this, there are tons of living in this zone. There are like dolphins, corals, tuna, and more. Below this surface zone, there is that transition zone. Sunlight sometimes reaches this layer of the ocean, but there is so little light that plants can't grow, and this zone goes from 200 to 1000 meters below the ocean's surface, and the last is the deep zone. This layer is so deep that the sunlight never reaches it, so it's completely dark. The upper layers of the ocean are warmed by sunlight. As you go deeper, there is less sunlight, so the water is colder. This drop-off in temperature is the cause of the thermocline. Next is mapping the ocean floor. In measuring the ocean depths and charting of the topography of the ocean floor, they use bathymetry. Echo sounder, also referred to as a sonar, it was invented in the 1920s and reflects sound from the ocean floor. And the multi-beam sonar, it employs an array of sound sources and listening device to obtain a profile of a narrow strip of the sea floor. Now, how will the multi-beam sonar works? An advanced multi-beam echo sounder set up on the underside of Eve Nautilus. This is a tool they use to create a detailed map of the sea floor. Maps which help us explore underwater mountains, locate shipwreck, and understand the ocean's topography. Now, here's how it works. The multi-beam generates up to 864 individual beams simultaneously. In a fan-shaped cover, a wide swath beneath the ship, when the sound wave bounces back, the multi-beam measures the time it takes for them to return to the ship. The longer it takes, the longer the distance to the sea floor at that spot. By putting together all the measurements from each beam in SWAT and combining 1,000 of SWATs, they create a 3D visualizations of the sea floor. The last topic is continental margins. We have here passive continental margins, found along most coastal areas that surround the Atlantic Ocean, not associated with plate boundaries and experience a little volcanism and few earthquakes. Starting with the continental shelf, it is under the sea water, but regardless of the thick continental rock, it is still a continent. So the width of our continental shelf just depends on the width and size of the continental plate. But regardless of where we are, all of our continental shelf are gently sloping. They are not quite flat. They don't really have a lot of ups and downs in them. But geologically, continental shelves are important because this is where all of our oil is for our transportation, and it really has a mineral and rocks deposits that we use for our electronics. Once we start transitioning our continental shelf, we will soon hit our continental slope. This is gonna be the exact edge of our continental shelf. Here, the slope is getting really steep as it transitions from the thick, buoyant crust of continent and that really thin, dense oceanic crust. But the bottom of our continental slope, we're going to get into a slightly more gentle gradient of our continental rise. It is not as flat as gentle as our shelf is, but it is nowhere near as steep as our slope. And here at our continental rise, because the gradient is starting to flatten back out, sediments is going to accumulate here. So, all of the sediment that is moved down the shelf and the slope is gonna end up being deposited in our continental rise. And a lot of time, it is going to end up in what is called a deep sea fan. This is where we have the sediment coming from our continents, especially from our rivers that are coming from the continents. And as those rivers discharge into the ocean, they are not just releasing their water, but all of the sediment as well. So that sediment is going to flow down this really steep slope and end up in these deep sea fans along our continental rises. So, all of this sediment water, this is called turbidity current. Turbidity means it's water with a whole bunch of sediment inside of it. So, when we have full of water, it is going to start eroding the sides. So, when we have areas where we have a lot of sediments in our water, we can have submarine canyons to develop. These are going to be really deep and steep-sided valleys that are cut into the continental slope, where all of the water and sediment were being moved downhill. Our active continental margins are totally different from the passive. The passive is accumulating sediment. It is just totally sitting there because it is not totally active. Our active continental margins, though, as the name suggests, are tectonically active. So in these continental margins that are active, we generally see subduction zones occurring. We're going to have lithosphere that is being subducted underneath the edge of a continent. This is going to create one of those deep ocean trenches. And we saw that passive margins surround the Atlantic Ocean, but our active continental margins surround our Pacific Ocean. We just have tons of subduction and volcanism going on here, but as we have subduction, the plate that is being subducted or pushed back into the earth is slowly going to start deforming some of the sediment and the rock from the overlying region and form what's so-called an accretionary wedge. An accretionary wedge is just triangular shaped area where sediment has been scraped off the other plate.
So, good day everyone. So, today I'm going to discuss the last topic of the ocean environment. So let's begin. Contents: marine life zones, other marine habitats, and seafloor sediments. So first, let's discuss the marine life zones. Oceanography includes biology. The presence and distribution of living marine organisms is affected by the chemistry, physics, and geology of the world oceans. Ocean plants and animals are influenced by available sunlight, distance from shore, water depth, salinity, temperature, type of bottom sediments, and dissolved oxygen. Availability of light, which is the photic and euphotic zone. So first, let's discuss the photic zone. So the upper part of the ocean into which any sunlight penetrates is the photic zone. So the clarity of seawater is affected by air bubbles, mineral content, decaying organic particles, and microscopic living organisms. Because these factors vary, sunlight penetrates to different depths in different areas. So the euphotic zone. So it's the portion of the photic zone near the surface where light is bright enough for photosynthesis to occur. So in clear water, this zone can reach a depth of 100 meters, but the zone will be much shallower in cloudy water. In the euphotic zone, small free floating algae, which is the phytoplankton, use sunlight to produce food molecules and become the basis of most food chains. So next is the Joyce resolution. So the Joyce resolution is the drilling shape of the ocean drilling program. The Joyce in the ship's name stands for Joint Oceanographic Institutions for Deep Earth Sampling and reflects the international commitment from the program's 19 member countries. The resolutions honors the HMS resolution commanded more than 200 years ago by the well-known explorer Captain James Cook. The giant resolution can re-enter hulls in the seafloor years after initial drilling. The ship's dynamic positioning system consists of powerful thrusters, small propellers that allow it to remain in place. Previous drill sites are located by bouncing sound waves between the ship's hydrophones and sonar beacons. A remote television's camera aids in positioning the drill pipe into the re-entry cone. So, during the cruise's hulls are drilled deep into the seafloor. The, the cores of sediment and rock that are recovered represent million years of Earth history and are used by scientists to study many aspects of Earth science. The ship is 143 meters long and 21 meters wide with a derrick that towers 62 meters above the waterline. So, a computer controlled positioning system maintains the ship over a specific location. So, the resolution is more about the ships that drill in the ocean floor or the sea floor. So, as what you see in the figure, that is there's a ship and there's a thruster ship drilled in the ocean floor or sea floor. So let's proceed though. So distance from shore, the intertidal zone and erratic zone. So before we discuss the two zone, the intertidal zone and erratic zone, let's discuss the aphotic zone first because I forgot to put in it. So I'm just gonna say it. So take notes about the aphotic zone. So although photosynthesis cannot occur much below 100 meters, there is enough light in the lower photic zone for marine animals to find food, avoid, avoid predators, recognize their species, and locate mates. But even deeper in the aphotic zone, there is no sunlight. Most of the deep ocean is lacking in light, except for the faint amount produced chemically by bioluminescent bacteria and animals. So the aquatic zone is this is a zone which is there's no light or lack in light, but except there is a bacteria or animals that called bioluminescent that gives a small amount of light. So as what I've said, this is the aquatic zone. The there is no sunlight or lacking in light. So let's proceed from that. As what I have mentioned earlier, the distance from shore, the intertidal and the neritic zone. So the intertidal zone is the area where the land and ocean meet and overlap is the intertidal zone. So this narrow strip between high and low tide lines is covered or uncovered by seawater with each tidal change. Here the land sea appear to be in constant conflict. Only a few species such as rockweeds, barnacles, chitons, and mole crabs can survive in the digestion of temperature changes. So next is the Neretic zone. So the Neretic zone is seaward from the low tide line is the Neretic zone. So so this zone can be very narrow or may extend for hundreds of kilometers. The entire Neretic zone is sometimes in the photic zone because sunlight may reach to its bottom. So, although the Neretic zone covers only about 5% of, of world ocean, it is rich in both numbers and diversity of living organisms. Photos- Photosynthesis occurs readily in nutrients washed in from land, and its bottom provides nest sites and protection. 90% of commercial fisheries are this marine zone. So let's proceed. So although photosynthesis cannot occur much below 100 meters, there's enough light in the lower photic zone or for marine animals to find food, avoid predators, recognize their species, and locate mates. But even deeper, the in the aquatic zone there's no sunlight. So this is what I have said earlier. That what is the aquatic zone. So it's just connected right. So this is the other marine now other habitats of marine life. So life zone, subdivision, and characteristic. So guys, you need to take a note of it. So because there's a lot of keywords. So let's start based on available lights, the photic, euphotic, and aphotic zone. So I already discussed this earlier. So photic has light, euphotic has enough light for photosynthesis, and aphotic is no light. So based on distance from shore, intertidal and intertidal and neritic and oceanic. So intertidal is as what I have mentioned that is between the tide lines with waves hit shore and also the neritic above continental shelf rich in biodiversity and oceanic open open ocean beyond shelf break. So next is the I with oceanic is I'm gonna discuss it later. So based on that pelagic and benthic, so I'm also gonna discuss it later. So pelagic is all water above ocean floor, organisms swim or float, and benthic is bottom of ocean, organisms attached to. burrow into or crawl on seafloor. And the last is abyssal, which is part of the basin depth. Deep sea bottoms that are called high pressure. And last is the other habitats, which is the estuaries, coral reefs, and hydrothermal vents. So estuaries is the rivers flows into ocean ti- and tidal cycles, and coral reefs, coral skeletons in tropical waters, and last is hydrothermal vents, which is the black smokers and chemosynthesis. So the black smokers of hydrothermal vents is a type of hydrothermal vent typically found on the seafloor. These vents are often referred to as underwater geysers. Black smokers can get up to 180 feet tall. So in short, the black smoker is underwater geysers. So chemosynthesis, it's a biochemical process that converts one or more carbon-containing molecules and nutrients into organic matter, using the oxidation of inorganic compounds as a source of energy. This process is different from photosynthesis, which uses sunlight as a source of energy. In chemosynthesis, methane or an inorganic compound such as hydrogen sulfide or hydrogen gas is oxidized to act as the energy source. So let's proceed. So oceanic zone, pelagic zone, benthic zone, and abyssal zone. So this three, the pelagic and benthic zone, is the depth. So it's the oceanic zone is the it's an exception because the oceanic zone is what I mentioned in the characteristics. It's right here. The oceanic zone is based on the distance from shore, so it's not part of the basin depth. Only the pelagic, benthic, and abyssal. So oceanic zone is the beyond the continental shelf is beyond the continental shelf is the oceanic zone. The open ocean reaches great depths, but usually has far smaller populations than the more productive continental shelf areas. So mid-ocean often resembles a biological lizard with a relatively organism present. So the oceanic zone is which, which is can, the open the open ocean reaches is the is open ocean and beyond shelf break. So it's different from the other three. So pelagic zone, a third method of organizing marine habitats uses ocean depth. Often ocean of any depth is called the pelagic zone. So animals in this zone is swim or float freely in the photic part of the pelagic zone. Is home to phytoplankton, zooplankton, fishes such as tuna, swordfish, and also sea turtles and dolphins. The aquatic part has changed species like viperfish and giant squid. So, benthic zone. This includes any sea bottom surface regardless of its distance from shore. So, it has a limitation because it says that regardless of its distance from shore. So, but animals such as sponges, crabs, and tube worms that attach to crawl upon or burrow into the seafloor are part of the benthic zone. In near coastal water, benthic communities usually get sunlight and have a bounty of organisms, bacteria, seaweeds, sponges, sea anemones, sea stars and worms, crustaceans and flatfishes. So abyssal zone. The abyssal zone is a subdivision of benthic zone and it's characterized by extremely high pressures, consistently low temperature, low oxygen, few nutrients, and no sunlight. Although rarely studied, abyssal plains are among the most extensive environment on Earth. So, the abyssal zone, which is also called the abyssopelagic zone, is the layer of the pelagic zone of the ocean. The abyss is a term derived from a Greek word which means bottomless. So take notes, abyss is from the Greek word which means bottomless. At depths at 3,000 to 6,000 meters, which is approximately 9,800 to 19,700 feet, this zone remains in acute darkness. So this part is very dark, and it's very it's very far. So let's proceed to the last topic, the seafloor sediments. So the seafloor sediments is also known as marine sediment or ocean sediment, refers to deposits or insoluble particles that have accumulated on seafloor. These deposits can include rock and soil particles transported from land areas to the ocean by wind, ice, and rivers, as well as the remains of marine organisms, product of submarine volcanisms, chemical precipitates from seawater, and materials from outer space. So types of seafloor sediments, the terragenous sediments, biogenous sediment, and hydrogenous sediment. So first, let's tackle the terragenous sediment. So heterogeneous sediment. So it consists primarily of mineral grains that were withered from the continental rocks and transported to the ocean. The sun-sized particles settle near shore. However, because the very smallest particles take years to settle to the ocean floor, they may be carried for thousands of kilometers by ocean currents. So heterogeneous sediment is deep sea sediment transported to the ocean by rivers and wind from the land sources. So heterogeneous sediments that reach the continental shelf are often stored in submarine canyons on the continental slope. Turbidity currents carry these sediments down into the deep sea. So next is the margin sediment. Wait, I have an addition of the heterogeneous sediment. So the heterogeneous sediments in oceanography, heterogeneous sediments are those derived from the uh, erosion of rocks on land, as that is, they are derived from terrestrial, as opposed to marine environments, consisting of sand, mud, and silt carried to sea by rivers. Their composition is usually related to their source. The position of these sediments is largely limited to the continental shelf. So let's proceed to biogenous sediment. So biogenous sediment consists of shells and skeletons of marine animals and plants. This debris is produced mostly by microscopic organisms living in sunlit waters near the ocean surface. The remains constantly rain down in the ocean, the sea floor. So, biogenous sediments come from the remains of living organisms that settle out as sediment when the organisms die. It is the hard parts of the organisms that contribute to the sediments. things like shells, teeth, or skeletal elements, as these parts are usually mineralized and more resistant to decomposition than the fleshly, soft parts that rapidly deteriorate after death. Macroscopic sediments contain large remains such as skeletons, teeth, or shells of larger organisms. This type of sediment is fairly rare over most of the ocean, as large organisms don't die in enough of concentrated abundance to allow these remains accumulate. One exception is around coral reefs. So the biogenous sediments comes from the living organisms, that is die or the hard parts of the living organisms. So the last one is hydrogenous sediments derived from water. So hydrogenous sediments consist of minerals that crystallize directly from seawater through various chemical reactions. For example, some limestones are formed when calcium carbonate precipitates directly from the water. However, most limestone is composed of biogenous sediments, so hydrogenous sediments is hydrogen. So it's like a composition or forming from the like sample limestones formed by which is came from. So occasionally chemical reactions occur that cause the substance or the precipitate that other solid particles when accumulate as heterogeneous sediment. These reactions are usually triggered by a chance of new conditions such as change in temperature, pressure, or pH, which reduce the amount of substance that can remain in a solid, I mean, can remain in a dissolved state. There is not a lot of hydrogenous sediment in the ocean compared to biogenous sediments, but there are some interesting forms. One type of hydrogenous sediment is significant for its economic potential is the manganese nodules. So, nodules are rounded lumps of manganese and other metals that form on the seafloor, generally ranging between 3 to 10 centimeters in diameter, although they may sometimes reach up to 30 centimeter feet. The nodules form in a manner similar to pearls. So the manganese nodules is like a pearl. It's like a pearl. So there's a central object around which concentric layers are slowly deposited, causing the nodule to grow over time. So it keeps on growing time by time. So the composition of the nodules sh- can vary somewhat depending on their location and the conditions of their formation, but they are usually dominated by manganese and iron oxide. So this is the formation of the manganese nodules. This one in here. So this came from the book. So nodules are widely distributed, but not all regions are equally promising for development. So that's what I have said earlier. So the manganese nodules also contain smaller amounts of other metals such as copper, nickel, and cobalt. The precipitation of manganese nodules is one of the slowest geological processes known. They grow on the order of a few millimeters per million years. For that reason, they only form in areas where there are low rates of lithogenous or polygenous sediment accumulation, because any other sediment deposition would quickly cover the nodules and prevent further nodule growth. Therefore, manganese nodules are usually limited to areas in the Central Ocean, far from significant lithogenous or polygenous inputs, where they can sometimes accumulate in large, numerically valuable metals. So that's all of the lessons of I tackled the seafloor and the marine life zone. So thank you for watching me, and God bless. Goodbye.